Today we're going to talk about limits at infinity, which means this. The limit of a function as x approaches infinity, or the limit of a function as x approaches negative infinity. So let me start by defining for you what that means. Okay? We say the limit of f of x as x goes to infinity equals L if for any epsilon greater than 0 there exists some m greater than 0 such that if x is in the domain of f and x is equal to or greater than m, then the distance between f of x and L is less than epsilon. Okay? Now let me show you a picture. Here's a graph of the function x squared over x squared plus 4. I'll write that down. Let's not write it right there. It's going to be in the way. Okay, so do you see in the picture what's happening there? As x goes to infinity, again, I want to point out, x isn't actually going to infinity. That's just what we call it. It's just that x is getting bigger and bigger without bound. Okay? What's happening to f of x? As x grows, f of x grows. Right? But it does have a bound. It's growing towards 1 and leveling off. Do you see that? And you know this from pre-calculus or college algebra, that dashed line is, what is that called? That's called a horizontal asymptote. Okay? And you need to remember that. That's something you need to know. But as far as this new definition goes, what's the definition saying? The definition is saying that, so the limit in this case, let's just write this down. In this case, the limit as x goes to infinity of our function equals 1. We can see that in the picture. I'll show you in a little bit how to actually calculate that. It's actually extremely simple. Okay, so what we're saying is that if you take a margin of error around 1, try to make this, I'm going to zoom way in on that, okay? Because I want to make this small, but I want you to still be able to see it. So if you take a margin of error around 1, and that margin of error is of size epsilon in either direction. Okay, then what the definition is saying, let's shrink back down so we can see the definition. What's the definition saying? For any epsilon greater than 0, so I drew an epsilon there, there exists some number, some positive number, such that if x reaches that positive number, then f of x should be trapped within that margin of error. Well, where is the m for that particular margin of error that I drew? Look, it's right here. That's kind of crooked. Let me redraw that. That's not much better. Third time's a charm. That's better. That's our m. You see, and once x gets past that, then f of x is now trapped within that margin of error around the limit. Okay, that's what the definition is saying. Now I'll write down the definition for the limit as x goes to negative infinity equals L, but you can guess from the picture how that's going to work, right? It's going to be the same. It's just that we look in this direction. This is for the limit as x goes to negative infinity. Our m is going to be over here, and x will surpass m in that direction. So m will be a negative number and x will be less than or equal to m in order for the distance between f of x and L to be less than epsilon. Okay? All that's left is for us to write that down. So let's go ahead and do that. Get some space here. We say the limit of f of x as x approaches negative infinity equals L if for any epsilon greater than 0 there exists some negative number such that if x is in the domain of f, and x is less than or equal to m, then the distance between f of x and L will be less than epsilon. And that's what's in this picture here. Okay? So that's the idea. Now let me just demonstrate for you. I'm going to prove that both of these limits, well, let's just do the positive one. Well, no, actually, I can do, for this particular one, because that graph is symmetric, you see how the right side is just a mirror image of the left side. So in this particular one, I can prove to you that the limits at infinity and negative infinity are both 1. Okay? I already worked out the scratch work, so I won't show you that, okay, because that's not what I want you to worry about. I just want to show you. And what I'm trying to say is I already found how big my capital M would need to be. And it turns out that capital M needs to be 4 over epsilon or negative 4 over epsilon. Let me put this in a picture. I already worked this out previously on my own, and I found those values. Okay, and I just want to show you how those values make everything fall together. Okay, so look at this. I just want to show you that, what color? Let's do this in gray. Okay, I just want to show you that if x is equal to or greater than 4 over epsilon, or if x is less than or equal to negative 4 over epsilon, then the distance between f of x and 1 will be less than epsilon. And I can do those both at the same time because, like I said, this one is nice and symmetric. This right here, x is equal to or greater than 4 over epsilon, or less than or equal to negative 4 over epsilon. It just so happens that we can do both of those at the same time by just saying the absolute value of x is equal to or greater than 4 over epsilon. Okay, so let me just show you that. I'm going to say, suppose that's true. Suppose this is true, then this will happen. Okay, it's very easy. So suppose, well here, I'm sorry, let's do this. For any epsilon greater than 0, comma, if the absolute value of x is equal to or greater than 4 over epsilon, which I just now realized that up above I wrote 4 over 3, which I sometimes do. I accidentally get my epsilons backwards and then they look like 3's. So let me fix that. Okay. For any epsilon greater than 0, if the absolute value of x is equal to or greater than 4 over epsilon, comma, then the distance between x squared over x squared plus 4 and 1 will do what? Well, let's see. First, I'm going to just simplify that. That's the absolute value of x squared over x squared plus 4 minus x squared plus 4 over x squared plus 4, which is the absolute value of negative 4 over x squared plus 4, which equals 4 over x squared plus 4. Okay, which is less than 4 over x squared, because this denominator is bigger than this denominator, which means this fraction is smaller than this fraction. Okay? And really quickly, I apologize for this. I just happened to realize something here. I meant to have square roots. I said 4 over epsilon. I actually meant the square root of 4 over epsilon. I'm sorry about that. Let me just throw that on there. Okay. And throw that on here. Okay, that's better. Okay, so let's look at where we left off. Where have we left off? We have this is less than 4 over x squared. Okay, well, if the absolute value of x, let me write this down. If the absolute value of x is equal to or greater than the square root of 4 over epsilon, then that means that x squared is equal to or greater than 4 over epsilon, which means that this fraction is less than or equal to this fraction. Okay, this denominator is equal to or greater than this denominator, means that this fraction is equal to or less than this fraction. And what does that last fraction equal? It equals epsilon. Okay? So there you go. That shows you that how I found my capital M, which was the square root of 4 over epsilon going towards infinity, and negative square root of 4 over epsilon going towards negative infinity. And if x gets past those lines, then the distance between f of x and 1 is less than epsilon. Okay? But here's the good news. For many functions, you don't have to do all that work because there's a tremendous shortcut for many functions. And I'm going to show that to you right now. Okay? Most of the time, functions with horizontal asymptotes are rational functions, which you've seen before, rational functions. Now, there's a tremendous shortcut for finding limits at infinity or negative infinity for rational functions. Okay? And it allows you to bypass all that epsilon stuff. So let me show you by doing an example first. Suppose you want to find the limit of, we'll do this rational function, x cubed plus 2x plus 1 over 4x cubed minus 2x squared plus 9. And let's do the limit as x approaches infinity. Okay? Now watch what you do. I'm going to divide every term by the highest power of x in the denominator. Okay? I look at the denominator only, and I choose the highest power of x. Some people look at the numerator too, and I used to. And then I realized I like it much better just looking at the denominator. Okay? What's the highest power of x in the denominator? Is x cubed. So I'm going to divide everything by x cubed. Okay? And then it will look like this. Okay. Now I get that x cubed from the highest power in the denominator, but I divide everything by x cubed, numerator and denominator. So x cubed divided by x cubed is 1. 2 over x divided by x cubed is 2 over x squared. 1 divided by x cubed is 1 over x cubed. Now the bottom, 4x cubed divided by x cubed is 4. Negative 2x squared divided by x cubed is negative 2 over x. And 9 divided by x cubed is 9 over x cubed. Now you let x go to infinity. Okay, look at on the middle of the top. 2 over x squared. The 2 is not changing, but the x squared is going to infinity. So what's going to happen to that fraction? It's going to go to 0. I'm not saying that 2 over infinity equals 0. There's no such thing as 2 over infinity. I'm saying 2 divided by something that grows infinitely big will shrink to 0. Okay? Same thing with the next fraction. And on the bottom, these two fractions, they disappear. So the limit, again, I'm not saying those fractions equal 0. That's why I didn't put an equal sign. I put an arrow. I said they grow towards 0. Okay? they approach 0. So the limit equals 1 plus 0 plus 0 over 4 minus 0 plus 0, which is what? 1/4. You don't even have to actually write this part if you don't want to. Okay, you see how easy that is? No epsilon, no capital M, nothing. And there's even a, so that's a pretty big shortcut, right? There's even a bigger shortcut on top of that. There's a shortcut on the shortcut, which is, look here, look at the original function. The top started with x cubed, right? Which is 1x cubed, right? Let's put a 1 there. The bottom started with 4x cubed. And look at this number right here. What's that number? 1/4. What did the limit come out to be? 1/4. What a shortcut, huh? And that happens anytime the degree of the numerator equals the degree of the denominator. Then the limit as x goes to infinity, and it would be the same if it was negative infinity. Same thing would happen. The limit ends up equaling what we call the ratio of the leading coefficients. Okay? Now let's look at one where the degree of the numerator is smaller than the degree of the denominator. And by the way, that one we just did would have been exactly the same whether x was going to positive or negative infinity. I'll even put in here plus or minus if you would like. Okay, so now let's do one like this. X squared plus 3x minus 7 over x cubed plus 2x squared plus 4x. How about that? And this is going to work out the same whether x goes to positive or negative infinity. Okay, the trick is 100% the same. I look at the denominator and I see the highest power is x cubed, so I divide everything by x cubed. X squared divided by x cubed is 1 over x. 3x divided by x cubed is 3 over x squared. 7 divided by x cubed is 7 over x cubed. On the bottom, x cubed divided by x cubed is 1. 2x squared divided by x cubed is 2 over x. And 4x divided by x cubed is 4 over x squared. You let x get infinitely large, either positive or negative direction, either way. What happens is this fraction will disappear, this one will disappear, this one will disappear, this one will disappear, this one will disappear. And what are we left with? 0 plus 0 minus 0 over 1 plus 0 plus 0. And what does that equal? That equals 0. And the reason why it came out to 0 is because the degree of the denominator is bigger than the degree of the numerator. Okay? All right. Let's do one where the degree of the numerator is bigger than the degree of the denominator. Let's do the limit of, let's do x squared plus 5x plus 4 over 2x minus 5. And we'll do the limit as x goes to, I'm going to go ahead and write plus or minus infinity. Okay. And what's the largest power in the denominator is x to the power 1, right? So I divide everything by x. X squared divided by x is x. 5x divided by x is 5. 4 divided by x is 4 over x. 2x divided by x is 2. 5 divided by x is 5 over x. Let x get infinitely large in either the positive or the negative direction. And this fraction disappears and this fraction disappears. Okay. So what are we left with? X plus 5 over 2. But x is getting infinitely big. So x plus 5 over 2 will get infinitely big, correct? Because in this case, looking just at what's left here, here, let me highlight it instead of circle it. Looking just at this here, the parts that do not disappear, you have x plus 5 over 2, right? The denominator is staying the same, but the numerator will get infinitely large, which means the fraction will get infinitely large, which means that this limit is either infinity or negative infinity. Okay? Which one is it will depend upon, is x going to positive infinity or negative infinity? So for this particular time, I'm not going to put them both together. Let's erase that plus minus sign. Let's just do x goes to positive infinity. Then x plus 5 over 2 will go to positive infinity, correct? And that's your answer. And if you did the limit of the same function as x goes to negative infinity, okay, you do it the same exact way. The only thing that will be any different is this thing here is the same, right? X plus 5 over 2, you see. The only thing that's different is as x goes towards negative infinity, that x plus 5 over 2 will go towards negative infinity. Okay? So that's going to happen whenever the degree of the numerator is bigger than the degree of the denominator, which in this case was 1. Okay? And I'm going to put a box here from the book to summarize all of that. Okay? What this box says is exactly what I just showed you. So let's just go through it. So you have here a rational function. The degree of the numerator is n. The degree of the denominator is m. Okay, and let's go through the three possibilities. If the degrees are the same, then the limit as x approaches infinity or negative infinity are the same, which is the ratio of the leading coefficients. Okay? If the degree of the top is less than the degree of the bottom, then the limit as x goes to either infinity or negative infinity will be the same, which is 0. And finally, if the degree of the top is greater than the bottom, then the limit as x goes to infinity or negative infinity are both infinite, but you do have to look at them separately, because one of them might be positive infinity or negative infinity, and the other one might be the same, or it might be the opposite. You know, you could have one of them positive infinity, one of them negative infinity, or both positive infinity, or both negative infinity. You have to look at them separately, just exactly like we did earlier. Okay, so I actually would suggest to you to go back and watch that part of the video again where I did those examples right before this box popped up. Okay, so you should know this shortcut that's in this box, but also you should also know how this shortcut worked, because we divide everything by the largest power in the denominator. On a test, I'm going to make you do that and show that. So you need to know how to do it. Don't just memorize this. You should memorize this box, but also you should be able to do like I showed up here in these problems. It's not hard. It's one of the easiest things in calculus. Okay? And before we close off, last thing. This same trick works even sometimes for harder functions too. Like, for instance, I'll just show this one to you real quick here. Let's do the limit of x over the square root of x squared plus 1. Let's do the limit as x goes to infinity. That's technically not a rational function because there's a square root in there. So technically, this idea here won't work, but it's practically the same. All I'm going to do is look at the denominator only. What's the highest power of x in the denominator? It's x squared, but that's inside of a square root, right? Well, that's okay. So here's what I'm going to do. Let's do the bottom first this time. So I'll divide everything by x squared. So it'll be x squared over x squared plus 1 over x squared. And then on top, I have x divided by, now here's the catch. Listen to this carefully. You're probably tempted to write x over x squared, right? But here's the thing. On the bottom, what did I divide by? I divided by x squared, right? At least that's what it looks like. But that was inside of a square root. So even though I said I was dividing by x squared, I was actually dividing by the square root of x squared, wasn't I? I was putting an x squared inside of a square root, so that was automatically the square root of x squared. And so that's what, whoops, that's what I put here too. Whatever I do on the bottom, I do the same thing on top. Okay? And so that equals the limit as x goes to infinity of x over, and I'm going to ask you a question. What's the square root of x squared? It is not x. It is the absolute value of x. Okay? Let's look at the bottom. What's x squared over x squared? It's 1. And what's 1 over x squared? It's 1 over x squared. Now we let x go to infinity. This fraction disappears. This fraction, what does it approach? Well, not even approach, actually. It actually equals, which I'll say that. One. Because x is going to infinity, which means we're going to be in the positive numbers, which means that the absolute value of x is x, and x over x is 1. Okay? All right, so what's the limit? The limit is 1 over the square root of 1 plus 0, which equals what? 1. Okay? This will get really easy for you after you do it a few times. Very easy. Okay? Well, that's it for today. Have a good afternoon.